Hi, Masood.
Everything visible?
Yeah, that works.
Okay, works fine.
I think I see the full screen, yeah.
Good.
All right, so welcome everyone. New edition of a new episode in the Noncommutative Geometry seminar. Saskia Roos, today talking about the twist of the free fermion.
Yes, thank you very much, and thank you a lot for the invitation to be part of this nice online seminar. So what I'm talking about is joint work with Matthias Ludewig. He's currently in Regensburg. And this is like the first step in a larger project we are currently working on. But I would like to introduce you to the project and to this idea we have. So what is the idea? The thing is, we would like to create some functorial field theory for the free fermion. And functorial field theory is kind of axiomatic mathematical formalism introduced by Atiyah and Siegel around 1988, and it should capture this quantum mechanics effects that we know from physics. But it's not, somehow it turned out to be not so easy to even formulate the most basic fields that we know in this axiomatic setting. For example, for the free boson, this was quite recently completely detailed, formulated by Kandel in 2016, so it's quite recent. And for the free fermion, there were completely partial results, so there have been a little bit die-free dealing with the determinant like of Michelson-Scott, made some other attempts with formulating it with projective spaces, and Müller-Szabo involved the index of the Dirac operator. And the thing is, while the free boson corresponds more to the Laplace equation, which is a nice positive operator, the free fermion corresponds to the Dirac equation, which is not positive at all anymore. And so we have this shear anomaly, which one phenomenon of is that eigenvalues can cross from being positive to negative and vice versa. And this could be, so this is not working quite. So this is our motivation to try to formulate it as a twisted field theory. So let me maybe shortly switch the modus. Yeah. So, yeah, okay, that's better. I'm sorry. So now, what is now a twisted field theory? Well, a twisted field theory, in the first place, it's a twist. So in our setting, this twist is going to be a functor from the Bordism category of spin manifolds into the bicategory of super algebras, or of Z2 algebras. And to be more detailed, this means that an object in this Bordism category, which is a closed d-1 dimensional spin manifold, is going to be mapped to an algebra, and a Bordism will be mapped to a bimodule. So this is the idea, and this is our goal. And then out of this twist, the next step is to construct a field theory, which is a natural transformation between the trivial twist, which just sends everything to C, and our constructed functor. So to be more explicit again, this would mean that the closed d-1 dimensional spin manifold is going to be mapped to a dy model. So there you see that it's going to be twisted by it. And something similar has happened to a Bordism. So this is not what a twisted field theory is, but for today, we are concentrating on the twist and want to construct this functor from the Bordism category to the super algebras in detail. And we will see that this functor has two parts: an huge algebraic core which will be coated by the analysis of the Dirac operator. So to see why the algebra enters, let us take a closer look on the Dirac operator. So a small reminder, what is the Dirac operator? So let us take a spin manifold and let sigma x be the spinor bundle. Then there's a canonical first order elliptic operator called the Dirac operator, which acts on spinors as follows. So if we have an orthonormal frame, then it's the Clifford multiplication after derivative in that direction, then just summing up over all the over the whole orthonormal frame. This is a quite famous operator, and you can a little bit think about it as the square root of the Laplacian. And for the remaining of the talk, we will always assume that our X is going to be a d-dimensional spin manifold with boundary, and near the boundary it has product structure, so that there's no problem with just gluing them together. And the y's are going always to be d minus 1 dimension closed spin manifolds. So the y's are the boundary manifolds and the x are the Bordism now, transmitting one to the other. So just to fix notation. Now let us take a closer look how Dirac operator and boundary interact with each other. So let us take a connected spin manifold with non-empty boundary. Then we have the kernel of the Dirac operator, which are the harmonic spinors, and we also take a look on the restrictions of the harmonic spinors to the boundary. And then there is a theorem that we indeed have an orthogonal splitting of the smooth spinors on the boundary between the boundary values of the harmonic spinors and Clifford multiplication with the outward unit normal of this Lagrangian. So in other words, now I slipped the word, you can view Lx as a Lagrangian with respect to the symplectic structure given by the bundle metric, and on the first entry we have inserted the Clifford multiplication of the outward unit normal. And this observation is going to be our ticket to the algebraic world. So instead of dealing so much with the Dirac operator, we will deal with Lagrangians. And as said, if we have borders, we also would like to glue them together. So we should also take in account what happens if we now glue two things. And there we have the following corollary, which can be proven. Now we take a closed d-dimensional spin manifold and cut in between. And then at this cut-in section, we see that these two Lagrangians, that these two boundary values for harmonic spinors coming from the left and right glued together nearly completely. So we have a small defect by this K, which is the restriction of the harmonic spinors on the whole closed d-dimensional spin manifold. So this K is always going to be finite dimensional, because as we know, the kernel of elliptic operator on a closed manifold is finite. And if we now imagine that this K is just zero, so that it's just the zero, so that the operator so that the Dirac operator would be invertible on this manifold, then we would see that these two things really would add up. So we have nearly a nice gluing, and we will see this nearly again now after entering the algebraic world. So let us now forget a little bit about having Dirac operators and spinors and so on, and just concentrate us on having a Hermitian vector space with a real structure. In this setting, a real structure means that we have an anti-unitary involution. just a bus. So for example, we could think of, an example would be just the usual complex conjugation in the complex numbers, something like this. And what we now also would need is now the opposite. This is the same Hermitian vector space, just with the real structures having now a minus. Now, and to this Hermitian vector space, if we have a real structure, we can associate now a Clifford algebra to it by saying that we want the Clifford relation being satisfied with respect to the bilinear formula form B, which is just our usual Hermitian product on the Hermitian vector space. But since we need a bilinear form, we need to make the anti-complex linear entry to be complex linear, and this is done by this our real structure. And this is now what going to be our Clifford algebra. So always when we see this notion CL of a vector space, and this is going to be the Clifford algebra that we are considering here. Now, and the Lagrangian in this setting is now a complex subspace such that its conjugate is exactly the orthogonal opposite, which in particular would means that the Lagrangian subspace is always closed. Now we need a little bit also to do a little bit of gluing. So let us take 3 Hermitian vector spaces, field structures, and taking Lagrangians in between them. So one between W and minus W1. Remember the minus W1 was the opposite. And L1, 2 now between 1 and 2. And now we would like to get from that Lagrangian between 0 and 2, a little bit like that these minus W1 and W1 would cancel somehow. And this is going to be the composition of 2 Lagrangians. And this is done by just looking which pairs really glue together in the sense that they really have a common middle point in W1. And if we are in finite dimensions, then everything is fine, and the composition of these 2 Lagrangians in that way is always again Lagrangian. But we will work in infinite dimension, and there this is not so clear anymore. In fact, the compositions of 2 Lagrangians does not have to be a Lagrangian again. So let me give you an example. So let us consider the space of sequences of a set, just quite integrable. And as a real structure, we just say that En is mapped to the E minus, and so we are just exchanging. So, and now for some alpha in R, we consider the densely defined unbounded operator Q alpha, which maps En to simply E to the alpha n times En. So, and for each alpha, if we take a look on the graph, then this will give us a Lagrangian in the space L to Z plus minus L to Z. And then the composition of these 2 Lagrangians would be just the graph of the composition of these 2 operators. And now we can observe 2 cases. Case 1, alpha 1 and alpha 2 have the same sign. Then everything is nice and fine, and it's just going through, and we have a Lagrangian in the composition. But if alpha 1 and alpha 2 have different signs, then this operator is not closed anymore. So it does not have a closed range, and we also in particular do not also have that the graph is closed. There are problems with the domains and with the range. So there the composition is not closed. It's not a closed subspace, in particular not a Lagrangian. In that case, if you would take the closure, it would be a Lagrangian again, but just considering the composition as defined as not a Lagrangian. So in infinite dimensions, we need an additional criteria under which we can be sure that composing two Lagrangians results again in a Lagrangian. And a criteria is given as follows. Namely, we take a look on the map where we take from the two Lagrangians S1 and L12 the W1 part and take a look at the difference. And what we showed in our paper is that if that image has closed range, then the composition is indeed a Lagrangian. This can be used by the graph theorem. So this is what we showed, and this is now one criteria which we're going to need. So back to the case. As said, we want the twist should map D minus one dimensional manifolds to algebras and the Bordism to bimodules. So where do we have our bimodules? Where do they appear? Well, we take a look at the exterior algebra of such a Lagrangian, and we can check that this can be viewed as a left module over CLW0 plus minus W1. How? Well, if we have now we define Clifford multiplication as follows. If we have an object from the Lagrangian, we just use the exterior multiplication. And if we have an element from the complex conjugate, then we do the interior multiplication. And since Lagrangians meant that the complex conjugate is exactly the orthogonal complement, these two definitions span all possibilities for the vectors. So this is how Clifford multiplication defined, how it turns out to be a left module, but we need a bimodule. How do we do this? Well, we split again the sum and put one summand on the other side as follows. Namely that we let W1 act on the W0 act on the left, and W1 is moved to the other side, and then we get the degree factor of -1 to the degree of the sigma if it's a homogeneous element. And these are going to be the bimodules that we need. So, and now, as with harmonic spinors, we would also be able to glue them together. So what does then now gluing mean? Well, we have our three Hermitian vector spaces with real structures. We have the Lagrangians. We know what the composition is, but how are they related? The naive attempt would be that the exterior algebra from the composition would be the same as taking the tensor product of these Lagrangian parts over the common algebra in between. And it should arise by just mapping the vacuum vector omega 02 to the corresponding tensor product. These vacuum vectors are just the ones in these exterior algebras. This would be a naive attempt, but this does not do the job. And the culprit here is this space K. Could you think of like a kind of a kernel? Because these are all the elements in W1 such that they connect a 0 from W0 to a 0 from that of W2. So these elements are all in between the 0 in the Lagrangian L02. So they are somehow vanishing. And this is the culprit why this naive attempt would fail. And I want to show you that this small calculation. So let us take an element from the space K with norm 1, then due to the Clifford relation, we can also write it as V bar dot V plus V dot V bar. Since we build this tensor product over the algebras, we can always move one to the other side. And now, since we know that this V is an element of K, means we know that the tuple 0 V bar is an element of the complex conjugate of a Lagrangian. And complex conjugates acts by interior multiplication. So in particular, it would lower the degree. But our vacuum vector is already a 0, a form of order 0. So this just vanishes. And therefore, if we have a space K like this, and if it's not trivial, then the thing that we would expect to be the unit vector in this tensor product is just 0. So in order to have an identification like this, we need to take this space K somehow into account. And there we see that this kind of twist or anomaly that appears really appears on this algebraic level. And how we can get an identification is now as follows. Namely, if the space K is finite dimensional, and if the map sigma, which we had known before, has closed range, then we can find a unique module isomorphism between the composition of the two Lagrangians and this tensor product by twisting this composing Lagrangians with the top space of the K space, and then map this top degree form just in between our vacuum vector. And this is now exactly the identification we obtain. So we can repair this if we take the space K into account, and this space K will appear also in the geometric setting. You will see later. So now for functor, it's not sufficient to have also this group, but we also need a coherence theorem. So meaning that if we now have 3 parts, so 3 Lagrangian, as 1, 1, 2, 1, 2, 3, then there are 2 ways how we can decompose them again. One is first at the one space, then at the second space, and one is at the second, and then the first. And in the end, it would be nice to arrive at the same thing. So in this coherence theorem needed, of course, to be checked. So we now get one more. We have Lagrangians. We assume that everything works fine, and we always have these nice isomorphisms with respective kernels. And then we do not the coherence for free, but we know that there exists a unique isomorphism to make this diagram works. And in the end, this diagram looks as follows. So in the top line, we start with the composing L03, and we compose the respective kernel in 2 ways. And first, we split at the W1 section. On the left-hand side, we first split on the W1 section, and then on the W2. And on the other side, we first split at W2, and then W1. And in the end, we see that really arrive at the same if we take this unique isomorphism above into account. So we see we needed to work quite a lot in that algebraic world to make all the things one that we want to have and that we need. But it will turn out that all the assumptions we made and all the things that we needed to repair are somehow naturally given by the analysis of the Dirac operator. So let us switch back to our Dirac operator. So going back, we have a d minus 1 dimensional spin manifold, and just to be sure that we all have the same spin structure in mind, the spin structure that we assume on our d minus 1 dimensional manifold is the one that we obtain when we extend it to a cylinder, then just restrict to one end. And now we want to put this all in the algebraic settings. So we endow now the space of L2 spinors, which is an infinite dimensional space, with the real structure given by I, Clifford multiplication with nu, and this is our outward unit normal. And now I just remind the notation, if we have now a d-dimensional spin manifold, which is a Bordism from y1 to y0, so it has the boundary y0 and y1 with opposite orientation. We again have the harmonic spinors and the restrictions. And the L2 completions are really a Lagrangian of the corresponding Clifford algebra. So far this analytical setup fits into the algebraic thing we just built up. So, and now if we have now the Bordism and now a cutting space in between this closed hypersurface Z, which splits it into x0 and x1, then you can just prove out from the properties of Dirac operator that this map sigma we had has indeed closed range. So Lx0 and Lx1 satisfy the assumption of the clear theorem, which means that if we compose them, then we obtain again the Lagrangian Lx. We've seen that these restrictions of harmonic spinors to the boundary always give us a Lagrangian. And this space K, which made our life a little bit difficult in the algebraic world, are now simply the solutions of the harmonic spinors that appears if a new closed component arises. So in the image, it's this XCLZ. So you see, if we cut, then this closed component is divided into two parts with boundary, and gluing at Z, we have one closed manifold, so no boundary anymore. And these geometric parts which glue together to a closed manifold are exactly the culprits for making the space K non-empty. So the space K corresponds to the space of harmonic spinors of new closed components. And since the space of harmonic spinors on a closed manifold is always finite dimensional, the elliptic theory gives us nearly for free that this space K has indeed finite dimensions. So we got all the ingredients that we need for the gluing theory just out of the boundary analysis from the Dirac operator. And thus we define now the twist as follows. If we have a d minus 1 dimensional spinifold, so boundary, we map the space to the Clifford algebra of the L2 spinors with the real structure that appeared 2 slides before. And a Bordism is now mapped to the exterior algebra of its Lagrangian. And now we also need to twisted again with the space K, and due to some technical issues, we have to split the harmonic Spinors into its positive and negative duality and consider the complex conjugate of the negative duality of the closed part. This had to break it down, the main reason is that we needed to consider a different complex structure, and the difference between these complex structures results in taking one of the dualities, the complex conjugate of one of the dualities. But indeed, this is, although it looks quite complicated, somehow quite a natural object for the Dirac operator is appearing. Namely, if we now assume that X is a closed manifold, so there is non-Lagrangian, then what we obtain is now the complex conjugate of the determinant line. So working out through this whole algebraic thing, we somehow naturally results in we naturally see the determinant line of the Dirac operator appearing here. And yeah, this was nice to see. This is also something that we want to have for the field theory in the end. So now, of course, we can define things like that, and it's still, but the definition is not the proof why this is a functor. So this still needs to be checked. So what does it mean? So we have now a Bordism from y0 to y1, and we assume we have a closed hypersurface cutting in between them. Then, of course, we have the parts in left and right, and we already know from the gluing theorem that we can have such an isomorphism. But there's one small difference, namely if we now simply recall that, we see that here for the definition of T of X, we added the tensor product with the harmonic Spinors to XCS of the closed part. But the isomorphisms we discussed in the algebraic part always only worked with the boundary value. So there was nothing in between. The thing in between was just having a direct sum. So there we still need to make an identification. So what we need here as an additional ingredient to really obtain an isomorphism is also now the restriction map to this cutting hypersurface set. So what you have in fact here is having this tensor product, then first restricting this closed part to Z, which is also scaled by its determinant of this restriction map, and then applying the isomorphism we know from the algebraic part. So we added a small geometric ingredient here. So we did not apply directly our algebraic results, but added this scaled restriction to that hypersurface that we need. I mean, of course, we could not put the scaling already in the definition because we did not know beforehand where we want to cut. And this makes a huge difference in the way this restriction map looks like. So we need to incorporate this restriction map into this isomorphism. But this is in fact the right thing to do. Because you see, if we now play the whole game with the coherence theorem, now with a huge manifold, where we now split at two different sections and want to look how all these Bordism behave, then the whole large diagram we had in the algebraic setting just simplifies to this small diagram. There we really have now this very nice coherence theorem that it doesn't matter if we first cut at y1 and that at y0, or first in y0 and then at y1. And what you really need to imagine here is that this large algebraic diagram we had beforehand really sits here in the middle. This coherence theorem is proved by relating everything to the diagram, to this algebraic diagram. And incorporating this restriction map is exactly the thing that corrects the additional unique isomorphism that we needed to add in the algebraic world. So to summarize it again, we started with the analytical setup and the idea to want to have a functor from the Bordism category of spin manifolds to superalgebra. We broke it down and we solved all problems in the algebraic world and saw that there's quite a lot happening. We needed to add a correction term. We needed to add an isomorphism to make all these Turing and coherence work. But then going back to the analytic world, the boundary analysis of the Dirac operator gives us all the ingredients and prerequisites that we needed so that it really just lies as a code over this algebraic field and unifies everything. And so that in the end, we really end up with this nice, small commutative diagram as we would like it to have. So far to the twist. And as I said, this is the first step. Now, what's going to happen next? As said, for a twisted field theory, the twist is the first step. So we are currently trying to construct a related functorial field theory, but as for the twist, there are various technical issues into where we need to verify how, for example, these determinant lines glue together, how these Lagrangians works in between, and so on. So there are quite a lot of issues that still need to be resolved. But having this twisted field theory is not the place where we want to stop. We have our dream, or more idea is a little bit larger. Namely, there are various spectral invariants for the Dirac operator that are interesting. And our idea is that we hope that we are able to extend this field theory to incorporate everything. So let me start from the top. We have the index of a Dirac operator. If we add boundary, then the Atiyah-Pauli Singer index theory brings the eta invariant of the boundary into play. Now, Dai Fried showed that if we have now an eta invariant on a manifold with boundary, we can view it as an element of the determinant line. And we added now that these determinant line also appear naturally if we are consider the boundary values of the harmonic spinors. And somehow we have all these single steps already worked out, and we believe that it should be possible to unify it, to really have a unifying approach, a unifying twisted field theory, where you really see where we start with our Lagrangians, that would lead to the determinant line, that would lead to the eta invariance, that would finally lead to the index. But having higher Bordism categories means having manifolds with boundaries, and there the analysis is getting more complicated. But as I said, this is a project that started 2 years ago, and we still hope that this is a long-going project where hopefully many interesting results coming out, and that we might be able to unify these spectral invariants in the end. And yeah, adding this hope, I finish my talk, and thank you very much for listening.
Thanks very much for your talk.
Thank you.
And then do a virtual applause. So I had, before, there are probably more questions, but I was wondering, just to make sure, the signature, the signs you're looking at, this is Riemannian, or?
Yeah, this is Riemannian. So far we are only looking for Riemannian manifolds. So these are all the Riemannian results. I mean, it's not so far ago. I mean, it was quite, I guess, 2 or 3 years ago that Christian Baer, together with Alexander Strohmayer, formulated an index theorem now for the Lorentzian manifold and APS index theory. And I guess it was just recently on Archive, they also put the version for the localized formula now. So I mean,
But that's
now
globally hyperbolic, I guess, right? So.
Yeah. In the Lorentzian case, the Dirac Operator is hyperbolic, but it's queen hyperbolic, so we have at least a well-defined Cauchy problem. So this already helps. But I mean, there's still a lot to be done. I mean, while for the Riemannian setting, we have a very nice and complete characterization for all these boundary values problems and nice boundary conditions, this is still a quite open field for the Lorentzian manifolds. So I would say that to do the same as we have done now in the Lorentzian setting, there's still a little bit of framework missing.
More questions?
Sorry, what happens when you vary metric?
What, please?
What happens when you change metric?
Not much. I mean, everything. The most important thing is that we still remain product at the boundary. If you change the metric in the interior, then your space K might change. But what we needed the most are these Lagrangians, the Lagrangian properties, but they remain the same.
Well, you have the same property, but the spaces themselves change, right?
Yeah, exactly. The space
so
themselves
the
change.
functors change.
Yeah.
So, okay.
So what about these Lagrangian subspaces? I mean, they're are they always finite dimensional because you're looking at kernels of Dirac operators, or are your manifolds typically locally compact only?
These Lagrangians of space, the Alex, they are infinite dimensional. I mean, they are like the half of the L2 spinors of the boundary. What is finite dimensional is the space, is this disturbing space K that might appear. And this is finite dimensional because if it appears as the kernel of a closed component. But the Lagrangian itself are all infinite dimensional. And this is why we needed to first figure out a characterization to ensure that if we glue these Lagrangians together, we again end up with a Lagrangian.
Okay. Okay, anything else? From around the globe? If not, then we thank Saskia again.
Thank you.
And well, we'll see each other next week again.
Yes, so I stopped the screen sharing.
Yeah, you can do that. Okay.
So,
Bye-bye.
Bye-bye, everyone.
Thanks.
Bye. And thank you again for having me here.
Sure.